Light is the fastest thing in the universe. Nothing can travel faster than the speed of light. It's the cosmic speed limit. In just 1 second, light could travel around the entire globe 7.5 times. And although we may think of it as being instantaneous, it's not. Like all things, it has a finite speed. And it's because of this that everything we see is in the past. I'm Damon Scotting, and this is Astronomical.
I'm here in Shanghai, where one of the world's greatest light shows takes place. A permanent fixture in the Shanghai skyline is the Bund Tower. Roughly 600 meters away from where I'm standing, I am seeing it in the past. Because of the finite speed of light, there is a time delay.
Across the river there, that's the Bund Tower, and that is approximately about 600 meters away from me. Now the speed of light is 300,000 kilometers per second. So when you do 600 meters divided by the speed of light, which is 300,000 kilometers per second, you get roughly 2 microseconds. That's the time delay between the time it takes for the light to bounce off that tower and reach my eye. So I'm seeing that tower right now as it was 2 microseconds ago. So the effects of light may seem insignificant on Earth, because we deal with such small distances, it's impossible for our brains to comprehend the time delay. But what about when we look towards the skies? What about when we look up at the moon? Now the moon is 384,000 kilometers away. And because light again travels at 300,000 kilometers per second, we can do the distance to the moon, 384,000 divided by the speed of light, 300,000 kilometers per second, and it gives us 1.26. That's the time delay. And we calculated that when the Apollo astronauts put retroreflectors on the surface of the moon. What that allowed us to do was bounce lasers off those retroreflectors on the moon and then receive them back on Earth. And the times we got were roughly 2.52 seconds, depending on how close the moon was to the Earth, because it changes throughout the year. And 2.52 seconds is 1.26 multiplied by 2. So what you've got is the time it took for the laser to reach the moon and the time it took for it to come back.
Moving even further out away from our planet, we reach the Sun. Now the Sun is 150 million kilometers away, which means it takes light 8 minutes and 20 seconds to reach us. So if our Sun was to disappear, we wouldn't notice it until 8 minutes and 20 seconds later. Nor would we notice being flung out into space, because we were no longer in orbit around the Sun. So at 8 minutes and 20 seconds, the distance delay is starting to become noticeable. Now what happens if we look out towards the other stars in our universe? Take our nearest neighbour, Proxima Centauri. It's 4.26 light years away, which means if you're travelling at the speed of light, for 4.26 years, you would then eventually reach it. So if you're travelling as fast as you could possibly go in the universe, you still wouldn't reach our nearest star for 4.25 years. Things get even stranger when we look further out. There's one star in the constellation of Orion that may already be dead.
Do you see that bright red star just here? This is a super red giant. It's called Betelgeuse, meaning shoulder. Now Betelgeuse is about to go supernova. In fact, it may do so anytime from now till about 1 million years or so. It's hard to predict. But the point is, it could go supernova any second. In fact, because Betelgeuse is 430 light years away, there's a fair chance it may have already gone supernova. But the light hasn't had a chance yet to reach us. Which raises the question, are we right now looking at a dead star? Has Betelgeuse already went supernova and the light hasn't had a chance to reach us? Maybe. Betelgeuse may have went supernova 429 years, 364 days, 23 hours, 59 minutes and 45 seconds ago. And if it did, then that means it's about to go supernova now. 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 Now, 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 now. How cool would it be if I shot a laser at a star and it blew up? It's like a dream. Ah, yeah, anyway, for any time from now to a million years or so in the future. So maybe it would... One can dream of blowing up a star with a 10-pound laser. Anyway, we move on. Do you see that faint fuzzy patch of light? That's not a cloud. That is an island. An island containing over 1 trillion stars. That is the Andromeda Galaxy. It's 2.5 million light years away, which means the light from this galaxy has travelled unimpeded through the vacuum of space for 2.5 million years, up until the point it hit the sensor of my camera, and now I've captured it. This is an image 2.5 million years old. The Andromeda Galaxy is the most distant object you can see with the naked eye. Okay, it's just incredible. It's incredible what you can do with just a camera. The Andromeda Galaxy isn't something that comes around once a year or once a decade. It is there 365 days. It doesn't go away. It's not something you have to pay to see. It's just there. When you go out and look up at the night sky, it's a free show. And it's possibly the best show in the world when you can see things like this. Over 1 trillion stars. Maybe there's someone, or maybe there's something orbiting around one of those stars who's looking back at us. This is my image of the Andromeda Galaxy. Now, there are over trillions of stars in this image, which means trillions of solar systems. So the idea that maybe in 2.5 million years' time, there is some other sort of being that's looking back at us and taking a similar image of the Milky Way is just mind-blowing. Or maybe in fact, they did the exact same as what I've done tonight 2.5 million years ago.
It truly is incredible the detail that can be made out with just a simple camera. But with the right tools, even more extraordinary images can be achieved. This is a gigapixel image of the Andromeda Galaxy. It is the highest resolution image ever taken of it. At this level of detail, this ocean of stars can be resolved to reveal trillions of individual points of light. At this scale, every single point of light is an entire solar system, as it looked 2.5 million years ago. Because the galaxy is so far away, it is as though you are travelling back in time to see things as they were.
Time travel might seem like something straight out of science fiction, but it's not. Time travel is real. In fact, you and I can both do it. Everyone can do it. And I'm going to show you how. There's 2 ways to travel in time. The first of which is to move. To have a velocity of any sorts, you are travelling in time relative to an observer. The second is to be near a body of mass. That's it. That's all you gotta do. By being on this planet, near the Earth, on its surface, you are travelling in time. Now it may look confusing, but I promise you it's not. In fact, in the next 60 seconds, you will understand how to travel in time. So, we have 4 variables. T prime, just here, is the time at which the observer, me, experiences time. T is the time at which our target will experience time. They're going to be the one moving. They're going to be the one time traveling. And then down here we have V for velocity, the speed at which they're moving, and C represents the speed of light, which is roughly 300,000 kilometers per second. It's very fast. For me, sat here watching them, I've experienced 1.00000000000000002 seconds, whilst they've experienced just one. I really hope that's the right amount. Okay. So as they walk past, every second that goes by, I experience it 20 attoseconds slower than they do. They are traveling forward in time. For them, they've only aged 1 second. For me, I've aged an extra 20 attoseconds. But 20 attoseconds is incredibly small. It's almost insignificant. It's 2 times 10 to the power of minus 17. That's 0.1602. But what if they were to move faster? What if they were running? Now, the fastest a human can run is just over 10 meters per second. But even then, the time difference that me and they experience is still so small. Now, what if I was to take a ride on the bullet train?
Now at these speeds you are moving very fast, but relative to the speed of light, this is almost nothing. In fact, if you were moving at this speed for 1,000,000 years continuously, you'd only experience 2 seconds time difference to a stationary observer.
The faster you move through space, the slower you move through time. The closer you approach to the speed of light, the slower time passes from your perspective. So to really appreciate the time dilation going on here, we're going to need to approach speeds much closer to the speed of light.
The time delay you experience increases exponentially the closer and closer you get to the speed of light, until you do eventually reach the speed of light itself and time stops.
Now this is the equation for time dilation based on your proximity to a body of mass. The closer you are, the slower time moves from your perspective. The larger the mass itself, the more time is dilated from your perspective. And the same applies here on Earth. The closer you are to the center of our planet, the slower time moves. Right now I'm on the surface, but if I was to go up a mountain or even a hill, time would tick faster than it would down here on the surface. And I know it sounds crazy to imagine this, and the numbers themselves are incredibly small, but trust me, even your head is slightly older than your feet because of this time dilation. But for this sort of time dilation, things start to get really interesting when you get near a body of extreme mass. I'm talking about the densest objects in the universe. A black hole. Another way to make time move slower for you is to go somewhere where there's a strong exertion of a gravitational pull. And there's no place in the universe where there's a stronger gravitational pull than around a black hole. In fact, there's a region around a black hole referred to as the event horizon, where the gravitational pull is so strong that not even the fastest thing in the universe, light, can escape its pull. And if you were to reach that point, if you were to reach the event horizon surrounding a black hole, time would literally stop for you. It would be the end of your universe. Time travel into the future is possible, but time as we know it right now only flows in one direction. You can't travel back in time, but you can travel forward.
There is no way to travel back in time, but there is a way to look back into it and see previous events, even events that happened billions of years ago. This is a time machine. A telescope is a time machine. The mirrors inside them are like buckets. They capture light from distant objects. The bigger the mirror, the more light you can capture. There's one telescope that has captured the most distant light we've ever seen. And it's also the most famous. This is the Hubble Space Telescope.
7, 6, 2, 1, and liftoff of Spaceship Atlantis. Final visit against the vision of Hubble into the deepest grandeur of our universe.
Houston, Atlanta, small program with the FCS channel.
Hubble launched 30 years ago, carrying the hope and wonder of our entire species. However, disaster struck just weeks into its mission when the world's most precisely cut mirror was noticed to have a small defect on its surface just 200 nanometers long. Problems like this weren't planned, but they were prepared for. Hubble was placed in a low Earth orbit, meaning potential repair missions were possible. This is footage from the final mission to service Hubble. In total, Hubble underwent 5 repair missions. It will likely function until 2030 before it slowly falls in its orbit around the planet and burns up in the atmosphere before it can reach the ground. But the images it achieved in its lifetime have changed our entire perspective towards the way we see the universe. Hubble has taken some of the most remarkable images in human history, one of which is significantly more important than any other.
Now this may be the most important image taken in the history of mankind. This is the Hubble Ultra Deep Field. Now the reason this image is special is because the Hubble Space Telescope pointed at an area of the sky that was seemingly blank, nothing inside of it. And what it found after exposing itself for just over 10 days was that there are 10,000 galaxies hidden away in this tiny little area.
What looks to be a tiny blank region in space reveals the true immensity of the scale of the universe. This image takes up an area 1/30 millionth of the sky, but its capabilities are still limited. Einstein showed us a century ago that gravity distorts light, and because of this bending effect it can magnify objects nearby, causing them to appear 10 to 20 times larger than they otherwise would. It's because of a group of several hundred galaxies named Abell 2744 that we are able to see one very special galaxy due to this gravitational lensing. This is GN-Z11, the furthest known galaxy in the universe. It is one of the very first collections of stars to ever form, and it would have looked very similar to this. Hubble has taken us to the very edge. It's allowed us to look back to just 400 million years after the beginning of the universe. But soon there will be a new space telescope that will allow us to see even further back into time. This is the James Webb Telescope. It is the largest and most advanced space telescope ever made. With it, we hope to see the very first light of the universe. Its precise resolution will allow it to resolve a penny from a distance of 40 kilometers. It was scheduled to launch in 2007 with a budget of $500 million, but due to a number of different factors, the costs of the telescope are now at $9.6 billion, with an expected launch date of March 2021. Its primary mirror is an enormous 6.5 meters, making it far larger than Hubble's at only 2.4. Whereas Hubble made most of its observations in visible light, James Webb is designed for infrared. Infrared observations are far superior when looking for older stars and galaxies, as they penetrate dust and gas clouds far better. Its infrared capabilities are expected to allow it to see the very first galaxies that formed just a few 100 million years after the Big Bang. The James Webb will also be an excellent addition in our search for exoplanets that may harbour life. The telescope's capabilities allow it to analyse the spectroscopy of a star's light that passes through the atmosphere of a planet, telling us its composition and if it is able to harbour life. The mirror is too big to fit inside the spacecraft that will launch it from the surface of the planet, so it needs to be folded. It also features the largest sun shield ever flown. 5 layers the size of a tennis court will protect the telescope from the heat of the Sun, Earth and Moon. One of the biggest reasons Webb is taking so long to launch is because of where it's being placed. Hubble was in a low Earth orbit just 540 kilometers away, whereas Webb will be placed in Lagrange Point 2, 1.5 million kilometers away. L2 is a point in our solar system where bodies experience equal gravitational pulls from the Earth and the Sun, thus moving in a constrained orbit, effectively around the Sun itself at the same speed the Earth does, despite being further away. The telescope will be pointing away from the Earth, Sun and Moon, protected by its sun shield, operating at a cool temperature of minus 220 degrees Celsius. The telescope will be making observations in infrared, so it's key that there is no distortion from anything nearby.
Now the James Webb Telescope has faced many setbacks, but it won't be long now before it does launch. And when it does, it's likely it will prompt questions we never thought to consider before. It will reveal wonders about the universe that we couldn't have possibly imagined without it. The James Webb Telescope is the ultimate representation of all that it means to be human, to be curious, to wonder, to have a relentless desire to know more. And I, for one, cannot wait for what it will show us. I'm Damon Scotting, and this is Astronomical. Was astronomical. This is the Hubble Ultra Deep Field. It was taken by the... Need to sneeze now. I can't start talking until I need to... Have you got that in slow-mo? No, now my nose is bleeding. Who the f bleeds? So, see this right here? This is living my lifelong dream of being a science presenter. This is what it costs. Nothing will stop me from achieving this dream, not even blood. That's worse. Look good, feel good. Tell you what, this water doesn't feel like salty or anything, that's cool. All right, let's take a seat. And where were we? That's right, I was about to show you these photos that I spent £12 getting printed off last minute and have now got blood all over. So these left, oh my god, my face stings. There is salt in that water. I'm just gonna say this as what it is, a f***ing disaster. This literally could not have gone any worse. Before I even got to do one take, everything stings.